let's assume that we have a model, there is a problem, we need to figure out what exactly went wrong. So the first avenue that we can go with is univariate drift detection. And what does it do? So first of all, it's going to capture the change in distribution of a single feature. And because it's going to look at the distribution of a single feature, with an ML, it's going to automatically kind of loop over all features in parallelized way, and you will see all features separately and how the distributions of those features is changing. But there's, of course, a few things that it cannot do, and the most important one is that it cannot detect changes in correlations between features or any really change in relationship between features, whether they're correlations or maybe something a bit less linear. And because imagine that you have a model with 70 features or 100 features, which is pretty standard in models that are deployed to production, if you look at every single feature separately, it's quite likely that some of them will shift, even though it doesn't impact performance or it's not the root cause of the problems that we might have identified with our performance monitoring. And that means that it can suffer from high positive rates. If you have 100 features and you want to do your monitoring daily, you'll almost certainly get a lot of false positives of things that are meaningfully changing, but they are not really the real problem. So you will just drown in alerts. And this is really one of the main reasons why univariate drift detection cannot be used as a kind of quality assurance tool, and you need to do performance monitoring. And instead, you should use univariate drift detections to really drill down on where the problem exactly might be after you've identified issues using performance monitoring. So now we have in our open source library 6 different methods for univariate drift detection. And at some point, I will make another webinar probably going over all of those in depth and discussing the pros and cons, but that is really going to take at least 1 hour. So this time I'm going to focus just on one that we recommend as a default and we have as a default in our library. And this is the Jensen-Shannon Distance. And why we recommend those is, first of all, it is a method that's quite good at detecting most of the significant shifts. So if you have a significant shift in your data, in your feature, it's going to be able to detect those most of the time, almost all the time. It is also quite robust against outliers, unlike some other methods. And few huge outliers or few anomalies in the data will not necessarily trigger that. So that already reduces the false positive rate or false alert rate. And of course, no method is perfect. That's why we have 6 of them, not just this one. And one of the main issues with Jensen-Shannon Distance is that it is potentially a bit too sensitive to small drifts. So you're still getting that false alerts here and there. But as long as you use it only as or mainly as a root cause analysis tool or kind of figuring what's going on tool, you should be fine. And now I'm going to go over this method a bit more in depth, talking about the inputs, the results, and the kind of intuition of how this method actually works and what it does. So let's start with practical things. So what are the things that we need to have? So the first thing we need to have is we need to get the features that we actually want to analyze, that we want to try to see if there's any drift. So we just provide column names for which we want to do our analysis. And then in our univariate drift calculator, which is kind of a high-level interface for any of the univariate drift detection features, we can specify, and we actually need to specify what methods do we want to use for drift detection. We can use more than one as a list. And the same we need to do for categorical methods, because some methods work only for continuous data, some methods work only for categorical data. One of the many strengths of Jensen-Shannon is that it actually works reasonably well for both categorical and continuous features, so we can use it for both. And now let's move to how this thing actually works. So here I have a kind of a presentation that should build a bit of intuition about what's going on. So we have here probability distribution functions. The reference one is, let's say, your test data, for which you know everything was fine and the distribution looked like it should look. So we have a bimodal distribution here, comprised of kind of two normal distributions, one centered around 0 and another centered around 5. And this is our reference distribution. Now, let's say that we wait a few weeks, few months, and we detect that there is some issue with performance. So then we're gonna want to compare our reference distribution to the, let's say, a week or a day for which we know that there is a problem. And for that, we'll look at our analysis distribution for a given feature. And we see that it has significantly changed. And there is one peak exactly at 0, and there is another peak this time at 10. So maybe again, some problem upstream in our data engineering pipelines when something was maybe not scaled or scaled inversely or just multiplied by 2 for some reason. And we see that there is significant change. And what JS actually provides us is an average distance between the distributions for these two distributions. So we see here that the analysis distribution is completely flat and reference distribution is quite high. So it's going to take this difference and halve it, and then it's going to do the same thing here between analysis and reference and the reference and analysis. So in essence, it's actually quite similar to KLR divergence, but the difference here is actually it doesn't only look from the perspective of difference between reference and analysis, but also from the difference between analysis and reference. So it's kind of like a KL divergence, but from both sides. And that is basically what our JS distance tells us. So now we kind of have a at least cursory intuition of how the method works. Now let's look at the results. So what we get here is our distance metric. So Jensen-Shannon distance goes between 0 and 1. And we see here that it is quite low. So we know that for this specific example, everything is doing fine. We have our threshold. If this threshold is exceeded, we know that there is a significant increase in our drift. And this threshold is generally automatically done by NaNML, automatically defined by NaNML using the variance of this Jensen-Shannon distance or any other distance in our reference data set, so let's say our test data set. And if there are some alerts, then of course we will see also the alerts.